Hey, John here. I was just playing around with this CRC generator module that I've been dabbling with. And I want to talk about this for two reasons. One, it's a useful CRC generator. And the other one is I wanted to talk about this generate statement down here and how this thing works in Verilog. So this is an example program, albeit far more complicated than it should be if the only goal here was to just discuss this generate statement. This is not a lecture on CRCs, and it's not going to be a complete lecture on generate either, but it'll be an introduction to the generate for loop as used while I'm implementing a CRC generator. A big thanks to everybody that supports my channel. I really appreciate it, especially all the Patreons and the VIP Patreons listed here. Thank you very much. See the links below the video in the description on YouTube if you want to know more about Patreon and supporting my channel. Thank you very much. All right, so first of all, let's talk a little bit about CRCs, just enough so you can find out what's going on. This is a list of a couple of videos by Ben Eater. If you watch my channel, you probably stumbled into Ben before because he does a similar kind of thing. He does a great video here on how CRCs work from the mathematic principles and why it works, what's good about it, why it is the way it is, and all that fun stuff. I'm not going to talk about this. This is the lecture to watch. This is better than a lot of the textbooks that I've seen at university level when teaching architecture and organization with a chapter on CRCs and stuff like that. This, I think, is one of the best lectures I know of on this, in that you can go from this and apply it. Okay, there are better lectures if all you want to know is theory. I'll give you that. But for what I'm going at, if you want to do something with this and make circuitry, this is where you want to start. Second, he builds a CRC calculation circuit with discrete chips, because that's what Ben does, and he runs it with some of these Arduinos. You can see it going here, and he sends data from one to the other, and he describes how it all works, and this is really great. You may want to watch this, but I point this out. I want to make really sure that you understand the method that Ben uses here is a style that directly maps from the mathematical theory right into the hardware. But, and this is why you need to understand there's a difference here. What happens if you do that is it is a little bit inefficient, and normally you wouldn't do it that way if you're making real hardware. And you'll see in a minute, the circuit that I'm going to show you here will read in one bit at a time using this input data port here, and it will make the CRC output value available immediately after each individual data bit arrives. And I want you to make sure you understand that that's the case, because Ben's does not work that way. This uses a technique where the data is available after you clock in a bunch of 0 bits after you've clocked in all the data you're using to calculate, all right? So his has to have a delay afterwards before the CRC is ready, but it's based directly mapped from the mathematical principles, and that's why he did it that way, I'm absolutely sure. Real circuitry would do it like this, because the CRC value is outputted from the circuit sooner, okay? I want to make sure you understand that, because if you go Googling around, you're going to see two different kind of circuits. And when I first got into this, I was very confused because the two circuits are very subtly different. And when you're looking at diagrams, like I just Googled CRC generator, the direct method. There's a direct method, and then there's an augmented zero method. And then people don't seem to agree on what to name them, but these are the two different kinds. Let's look very closely at these two diagrams. The circle with a plus is XOR operation. So this right here is a 2-input XOR gate with the data from here and there, and the output of the XOR goes into this circuit over here. This entire thing is just a bunch of flip-flops. They don't show the clock here. Each time there's a clock. This is just a shift register that shifts everything around like this. And that's how the CRCs work. When you build them to accept data 1 bit at a time in a serial fashion. You can do CRCs in other ways, but if you're going to do it in a serial fashion, you build a shift register and do this. It's a very simple circuit. Other ones are more complicated, very different ways of doing this. I'm only going to talk about the bit serial style circuitry here today. And that's what Ben talks about too. Ben implemented the kind that you see in this diagram up here. Let's look very closely at this diagram. What this is showing, this is the least significant bit, D0, D1, D2, D3, and so on up to Dn minus 1. Okay, so what you're doing is data flows in here in this circuit. There's an XOR gate. The inputs to this XOR gate come from the output of this guy. I don't know what these switch thingies are for. This is probably part of a larger conversation where they can disconnect this so they can use it as a shift register without the XOR gates, maybe. I don't know. But in this case, just assume these switches are closed, all right? The idea is in this kind of circuit, and this is what Ben does. You can hear all about it in Ben's video. There'll be links below mine to his. The data comes in, goes into an XOR gate, and one of the inputs of this XOR gate, and this one, and all the other XOR gates in this design come from the most significant bit that shifts out the left. So each of these XOR gates has the input that's coming from the serial line, the least significant bit here. This one has the least significant bit and the most significant bit coming around like so, all right? So think about what that means. The data comes in from the lesser bit, and you're shifting left on each clock, okay? And the XOR gate simply will invert the data as it flows through here when the most significant bit is 1, because that's what an XOR gate does. If one of the inputs is 1, the output will be the opposite value of the other input. It's sort of like a gated inverter. If it's a 2-input XOR, that's what they do. If you don't believe me, go look up the truth table on Wikipedia or something like that. Convince yourself that that's true. So this is what's happening. If the most significant bit is a 1, when you shift left, those bits that hop to the left through the XOR will be inverted. And that control is solely based on the value coming out of the most significant bit of this shift register. Now let's look at this one. It's drawn in a terrible way, and it's shifting the other way, and it turns around and comes back the other way. I should have drawn these out by hand, but I didn't want to. I just wanted to put this video together. Bear with me here. Look what's happening. Up here, the data in goes through this XOR and into the least significant bit. The other input of this XOR is hardwired to the most significant bit, comes around like that, okay? Same is true here. Here's the least significant bit. Most significant bit in the data in, one could say so far these are the same circuit. Here's where it differs. The output of this XOR gate is what drives all the other XOR gates in this circuit. Very, very different than what happens if you just simply take the most significant bit and run it into each one of these other XOR gates in the circuit. Okay? Ben's video does this. Watch his video, understand how it works. If you do this, what happens is you shift a bunch of bits in here that represents a message upon which you want to calculate this CRC value. And if you're going to use this technique and you have a 10-bit CRC value, when you're done shifting the message in, you have to shift in 10 zeros. After that 10th zero has been shifted in, you can then use the value in all these flip-flops, and that will be the value of your CRC. In this technique down here, the math is a little bit different. In this case, this is a 16-bit CRC, okay? When you shift in a whole bunch of message bits, after you've shifted in the last bit, you can immediately read the value out of all these flip-flops, and that will equal your CRC, all right? So the only difference in this schematic between the one up here and the one down here is that the most significant bit goes through an XOR gate to all the other XOR gates. This one, the most significant bit, goes directly to all the other XOR gates. Okay? If you don't follow this, stop the video and sketch this out by hand to make sure you know the difference. This is a big deal because I'm not going to get the same results that Ben does because I use a different technique. Okay? All right. Let's, what do we got here? This is the main module in this project web page. I'll put a link to this GitHub repo below so you can grab the code if you want to. So here's my checked out copy, and I've got 2 different test benches. Okay, remember, I wanted to talk about implementing a CRC using the model I just described, and you'll see the code when I open up this file here. And I have 2 different test benches, and this is where this generate stuff kind of comes into play. Now, I want to be able to use the same CRC module, and I want to be able to parameterize. I'm going to use parameters to set it so that the same module can be used to generate 16-bit CRC calculations, 8-bit 32-bit, whatever. Okay, I got a parameterizable module. So I have 2 different test benches. I simply copied the 8-bit one into the 16-bit one here. They're exactly the same, except I have different parameters when I instantiate the CRC module here. Okay, so let's start with first assuming you know what a CRC is, and secondly, if you didn't realize the difference of the 2 different styles of calculation, you're aware of it now, and you will see that the circuit in here that calculates the CRC, this one line is the whole thing right here, okay? You can see I got a clock, and every time the clock ticks, the CRC shift register shifts to the left, and there's an XOR function in here, and we use this logic here to decide whether or not we're going to XOR it with the thing on the right or not. And keep in mind also that the XOR function is, as I said before, it is merely flipping a bit as it goes, or it is not. Okay? So that's what's happening in this line right here. The parameterizable part up here can be used. The default is to calculate an 8-bit CRC. You got a polynomial if you know how CRCs work. If you don't, go watch Ben's video and you'll understand what the polynomial's for. There's an initial value for the CRC generator, and there's a parameter that says I want to XOR the resulting value with some constant. These are all standard CRC features. There's also the notion of reflecting the output bits, and this is where the generate will come into play. Now, what Ben does not talk about in his video is he talks about the initial value and why you need it. The short of it there is you do not normally want to make your initial value be 0, because if you use a CRC to validate a message's content, and the message starts with binary zeros, the CRC will not indicate whether the initial zeros are missing or not. He explains that in his video. I'll let you go look at that if you don't understand it. The XORing of the output, he doesn't even mention that at all. This is a feature of some standard CRCs that I use to test my code, and we'll look at that in a minute, where I got that. There's a bunch of websites. CRCs are an enormously common mathematical thing, and everybody everywhere seems to have an opinion on them and ways to generate them. And tons of libraries. It's a big, huge thing. They're common in all kinds of security applications and things like that. They're kind of like MD5 and things like that. And MD5 is not a CRC, but it's a related kind of an idea where you've got this check signature of some kind. All right? Ben doesn't talk about reflection either, as far as I know. This is important because when you actually apply a CRC, you need to know both ends have to agree on the order in which the bits are going to be sent from the sender to the receiver. Okay? So do you send the big endian bit first or the little endian bit first? So it's reflected. If you big endian or a little, you need to reverse the order of the bits. Okay? So one of the configurations to this thing here is once the CRC has been calculated, do I want to make the value in the CRC output register a big bitwise, big endian bitwise speaking? So is the most significant bit on the left or the least significant bit on the left? Okay, that's what this reflection thing here is. There's also a notion of reflecting the input, which I don't implement in here because this module is set to receive one data bit at a time in whatever the natural order of the bits are. Okay, so we'll look at one of these configuration websites here in a second. What do we got? I got a link in here. See the crccalc.com? Here's a website that says here's a bunch of CRC algorithms, some of which I have in my test bench here, okay? You can type in a message up here, and then you can click on one of these things. You can say, okay, show me this in hex. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9 in hex. So you get 31, 32. This is ASCII, okay? 33, 34, these are, 1 through 9 in ASCII. So this is 9 digits, obviously. And these are the ASCII encodings of those 9 digits. So if I click on CRC8, what happens is this is going to only show the 8-bit CRCs out of all the ones that it has pre-programmed to show you. If you click this, it'll also show you other names by which the same CRCs are used. So the DAO CRC and the 8 Maxim and the 8 Maxim DAO, all these are different names for this same set of parameters. These parameters in here, or at least some of them, you'll notice is it reflect out, the XOR out, the initial value, and the polynomial. These are the parameters that I use to configure my CRC generator. And this is why I can generate any 8-bit CRC. You just change these values. Do you want to XOR the output? You want to reflect the output? Yes or no? Do you want to XOR the output? What do you want to XOR it with? All zeros or some other thing? So in here, where's XOR out? So if I want to implement a CRC8 auto SAR, I would XOR the output with all ones. Do I want to reflect the output? No. The reflecting of the input we'll talk about when we look at the test bench, because as you know, my module, as I said before, does not have a way to reflect the input. You have to, the test bench and the data source simply has to clock it in the proper order. So if it's not supposed to be reflected, it needs to clock it in that order. If it is supposed to be reflected, whatever is giving you the data, and when you send it to my CRC module, it has to send it backwards. Okay? It's up to the data source. And this is why they have different values in here. If you think about it, if you're going to hook up like an RS-232 UART, and you want to send a bunch of data, and you're going to calculate a CRC on that data, and you want to use one of these standards, and you're sending it in RS-232, what do they send? They send the least significant bit first. And you got a start bit, then you got the low order bit, the next one, and so on. And then you got a parity and a stop bit and all that other fun stuff. So it turns out it would be very nice if you're going to calculate the CRC while the data is arriving out of an asynchronous UART that sends bits the least significant bit first, that you get a proper CRC that accepts the data in the native order as the data arrives. Otherwise, you're going to have to load up like an entire byte, or if you have a CRC 16, you'd have to read in 16 bits, then you'd have to flip them all around, then you'd have to clock it into your CRC generator, which is utterly stupid if you're going to implement something like a UART inside of your FPGA and the CRC generator inside your FPGA. It would be very nice to be able to use, if someone does you the favor, right? The guy on the other end of the wire has to agree with all your math and what you're going to do with it here, okay? But if they're going to send the data in little endian order, you should be able to pick a CRC and use it that expects the input data to come in little bit endian order, okay? So that's what's going on with the reflecting input. If you're going to design a new system, just choose one that allows you to calculate your CRC in the native order of the bit arrival. Ethernet is big endian bit order, so you're going to want to use one that is, I don't remember off the top of my head if reflected is big endian first or little endian first. I'll have to look and see what my code does to remind myself in the test bench, because I actually have some logic that reverses them in there to make sure that these are correct, okay? And again, your initial value shouldn't really be 0. It kind of depends on your test or on your usage case. Anything that's not 0, in my opinion, is better than something that is 0, unless you want to ignore all the data that arrives at the beginning of the message that is set to 0. Again, Ben talks about that somewhere in his video. I remember seeing it in there. If you do not initialize your CRC register before you clock in your message, it will ignore all leading zeros prior to the first 1 bit in your message, is the short of it. So these are useful if you want that feature. Otherwise, they're not a good idea, okay? You probably want to have a non-zero value if you want to know that all the leading zeros are present in your message and the right number of them are there, okay? And you can see a whole bunch of different types that are either all ones or some other value. As I understand it, there's not really a huge benefit of choosing some random value in here. Any non-zero value should cover that use case. All right. So what do we got here? We've got a polynomial, and Ben talks all about the polynomial. So you need all about that. And the way you read this thing is the check and the result is the same in this scenario. What happens is, if you send an ASCII message, 1, 2, 3, 4, 5, 6, 7, 8, 9, and you're using this algorithm, what should the result be? What is the CRC 8 AUTOSAR of this input message? Okay, it should be a DF with these parameters. All right, polynomial encoded like this represents, there's a 1 bit in here for each part, each stage in the shift registers, okay, where there's supposed to be an XOR gate. All right, so in this case, we got a 16-bit CRC. Therefore, you have a 16-bit polynomial by definition, okay? And there's always an XOR gate at the first, on the way between the data into the first gate. This will always be here, okay? Therefore, every one of these polynomials is an odd number. If anybody ever gives you a polynomial that's not an odd number, that's wrong, okay? It's just mathematically not correct, okay? So there's one little way you can check to see if somebody's lying to you or doesn't know what they're talking about. Why? Because there's always an XOR gate between the arrival data and this guy down here. So this one here represents the least significant bit in the polynomial. So the polynomial for this will have 3 bits set and a 16-bit hex value, or 16-bit binary value, all right? So there'll be the least significant bit here, there will be one here and there. So what will that be? This is like, bit 0 is always going to be an XOR gate, right? So there would be an XOR here if there was a 1. Oh, we got 1, 2, 3, 4. So this is going to end, the polynomial will end in a 1, because there's their 4 bits, the least significant 4 bits of the polynomial hex constant, if you express it in hex. The next digit in your hex, if you're going to give them a 16-bit polynomial in hex, this will be a 2, because it's between the 0 and 1 bits of this 4-bit hex nibble. Okay, this one down here, 1, 2, 3, 4, will be a 0. Okay, and then the most significant digit in the hex polynomial will be a 1. So this would be, as a hex constant, you'd have a 1, 0, 2, 1 for this polynomial here. And let's see if there is any in here for CRC 16s that is a 1021. Maybe that's a standard thing, or they just made some random thing up. Polynomial. Oh, look at this. I bet that website that has that picture is generating, that's a polynomial generator for this one, whatever CRC 16 dark and so on is. Okay, so this is how these things all connect up. When I was learning how to do with CRCs and whatnot, I found this very disorienting. Okay, so a lot of review here. I'm sorry if you already know a lot of this stuff, but I don't think Ben gets heavily into this part because he's talks a lot about theory, some application, but he doesn't get into a lot of these other things that go on with these CRC implementations. Okay, so I've got 8 bits, I got 16 bits, and a module that can do either one based on a parameterization that includes how many bits are in your polynomial, as well as the polynomial value, whether you're reflecting and XORing and stuff like that. Okay, and that's given here. The bits come in one at a time, synchronized to this clock. You reset it whenever you want to start sending a new message and calculate a new polynomial. The data here has to be valid on the rising edge of the clock to send in the data. The enable signal here allows us to continuously clock the module. And if and only if the enable's high on the leading edge of clock does data get ingested into the CRC module. In other words, I can clock in a bunch of data bits when the enable's on, then turn the data enable, or rather turn the enable line off, continue clocking this while it won't do anything at all. It'll just hold because it's not enabled. Then I can re-enable it later if I want and resume sending more data, the same message, okay? That's what the enable bit's for. And the CRC out is always true at any point in time as long as we're clocking and we're not reset. Okay, when it's reset, this will be written, you can see the logic right here, to the initial value, all right? And that makes sense. Whenever you reset your CRC generator, it takes your init value, okay, which is the this column here. So we're looking at 8 bits in the default configuration of the module, right? So the initial value, and the one that I chose is 0. I think this is I call that whack-a-mole every time I see it. The WCDMA is actually one of these in here somewhere. Right here. So what do we got? The initial value is 0, okay? And you can see the polynomial is, I believe that there, yeah, 9b with a, you reflect the input, reflect the output. You do not XOR the resulting value with anything, and you should get a 2.5 as your result if you clock in 9 bits like this in the correct bit order. Okay, now, yeah, when we look at the waveform, you'll see the CRC out is available immediately rather than after a bunch of zeros are clocked into the circuit, which is useful if you cannot wait after the message has arrived before, you know, more data might be arriving right away, and it can cause a problem, which is why you don't normally do it that way. A couple of wires and things for the circuit. As I said, when it's reset, we put the initial value in this, we preload the CRC register as appropriate. And whenever it is enabled, you can see here what we're doing is we're taking bits minus 2, so that's not the most significant bit. It's the one over to the right. And we're throwing away the most significant bit is what we're doing. And we're shifting a 0 into the least significant bit. Now remember what the circuit said. The least significant bit, when you shift it, is not 0. It's supposed to be set to, no matter what kind of CRC you're using, the most significant bit XORed with the data bit is supposed to go down here. Okay? Now think about that. Most significant bit XORed with the data bit here goes into there. Okay? Now I set it to this. I set it to 0. Then I XOR it with this. Okay, so let's look and see what's going on here. I take the XDI value, which comes from up here, and we'll look at that in a second. If XDI is true, I XOR the entire CRC register after it's been shifted left, and a 0 is put in down there. I will XOR the entire thing with the polynomial, or I will XOR it with 0, which effectively doesn't do anything at all. Look what's happening. This here, this signal right there is XDI. We're going to see XDI right now. XDI is the most significant bit XORed with the current input data bit. Well, that's exactly what this is. So this line here is my XDI signal in my design. Okay, that is loaded as is into the least significant bit. Now, how does that work if I put 0 in there? Well, if XDI is 1, I know that I want a 1 in the least significant bit. And because I told you earlier that all polynomials have the least significant bit set to a 1, then I know for an absolute fact that the value here will be XORed with something that has a least significant bit equal to 1, and anything, anytime you XOR a 1 with a 0, you get 1. So when XDI is equal to 1, this will cause the least significant bit to become 1. Okay? If you're not following, go ahead and stop it. Think it out. It's true. Okay? Any of the other bits in this polynomial, based on however you configure it, again, if XDI is 1, will cause each one of these bits to be inverted. And that's exactly what happens. When you shift it to the left and XDI is a 1, during or after the shift, you want to flip that bit. So in this case, the polynomial has 1s in this bit position and this bit position, and as always, the least significant bit position. So if XDI is a 1, I want to flip this, which I hard-coded to a 0, will become a 1, which is what you want. And if it's a 1, I want to invert the value I shifted into 6 from 5. That's exactly what will happen, and so on. Okay, for any bit that's a 1 in the polynomial, that's what will happen. If XDI is ever 0, then, if you think about it, this XOR gate has one of the inputs as 0. And this is 0. So I do not want to set this to a 1. I want it to leave it alone and be a 0, which will happen when XDI is 0. Obviously, it'll be 0. One of the inputs to that XOR gate is a 0. Therefore, 5 moves over to 6 without being touched. Same with this, okay? This one line implements that whole circuit using this style, the so-called immediate CRC implementation, rather than this 0 augmented one up here. It's very similar, but they're not the same. So we're doing this again. I can't beat that one enough. So this is how I decided to do it, okay? So all we're going to do is XOR it each time with the poly if XDI is 1. Otherwise, we're going to leave it alone, and we're going to just keep shifting it left. That's the whole ball game right there. And this is kind of tricky. It's hiding up here. Make sure you notice that. If you look at the code, we'll come back to the generate in a minute. Here's where we do the XORing of the output resulting data. Now, either you're going to take the resulting CRC value that comes out of this here, okay, and you're going to XOR it with the XOR out value, or XOR out value will simply be 0, which means you will not XOR it, you won't do anything. And that matches this table over here. You're either going to XOR it with 0 or all ones or a 55 or whatever the specific algorithm you want to use calls for. And the dogs say hi. Okay, so that's what this is doing here with the XOR. That leaves us with the generate, and that leaves us kind of with the test benches and stuff like that. So now let's look at the test bench for CRC 8, and then come back and look at the generate. Okay, so the 8 and the 16, I'll leave the 16 as a task for the viewer. The 8-bit version here has is a whole lot of different ones, all of which are named based on like ITU out and so on. They're all based on the names that you see in here. There's the whack-a-mole, and there's there's the ITU and the AutoSAR and Bluetooth, the CDMA 2000. Here's your CDMA 2000 and so on. When I do these, look at these. Bitwise little endian data arrival. Bitwise big endian data arrival. Look what's going on here. The whack-a-mole and the ROHC and the Maxim and so on. Where is the whack-a-mole? It's down here. This guy. See how he's got a true and a true for the reflect in? That confirms that if you reflect the input, you want to send the least significant bit of each one of the bytes of the message first. If it says false, like CRC 8, then you want to send the most significant bit first for each byte in the message. So I know I got an 8, and you just saw the WCDMA. See how it says data ref here? And the other ones, like CRC 8, okay, will say just data. Now, the data port on the CRC module for each one of these instantiations, the input is called data. It's 1 bit data at a time. So you'll see below in the test case, I generate from my sample data, which is the same one that the website uses for the default tests, okay? So all these values, the polynomial, you'll see down below the check values, will all match what you see in that website. Make it nice and easy. This value, this register variable, okay, this constant, what it is, what I'm going to do is this is a bunch of 8-bit values, and each one of these 8-bit values, okay, strung in one after another, will represent one big bit array whose length is 9 characters times 8 bits each, okay? Now we got to be careful, because what's the order of all these bits if I initialize it this way? It might have been easier to just initialize the whole thing in raw binary, although that would have been an enormous thing to type in. I'd probably do it wrong. So what happens here is you can see the artifact of this whole thing. This check data vector is one big bit array, and when you go down here and you look at the test logic, what happens is the main logic is in this combinational circuit here. We'll take a bigger picture of all the other pieces in a minute, but look what's happening here. We got index and index reflected, and we have data and data reflected. So what happens here is data represents most significant bit first for each one of the bytes in the test vector above, the nine characters of ASCII. So if it is not reflected, we want to send the most significant bit first. And we just simply count the index value from 0 up to 9 times 8. We'll see how that works up here in a minute. And that's the bit we want to send. But if we want to send it reflected, what we want to do is send the least significant bit first for each one of the bytes up to the most significant bit. So the math up here calculates, this one's just going to count from 0 up to message length -1. Okay? And what are we going to do? What we're going to do, we're going to say if we enable, let's go back up to the top and see how the enable and stuff works up here. What do we do? When we fire up the test case, reset is 1, so right out of the gate, reset is active, clock is 0, and everything else is initialized to 0. We got a bunch of stuff in here. We have a counter, the index, and the index reflected values that you saw earlier. This is kind of dumb. I should have made the 7 based on the number of bytes in the message. I'll leave that as a task to the user. If you want to do more than 256 bits in your array, remember these are the bit numbers. You might need bigger reg variables for this. The reset period of 4 clocks, you'll see how that's used down below. Each one of these instantiations, I already said earlier, based on all the parameters that you see in the website, and you've got the clock reset, either doing reflected or non-reflected data. You're going to have this enable signal, and then we look at the output, which we send into these the output ports. In each case goes to its own variable here, and we'll see how we use that below in the test bench. Same thing with these non-reflected ones. The only difference is you got data instead of data ref. And what are we going to got? We're going to open up the output file and dump everything as usual. Wait a little while. This probably is supposed to be set to this up here, reset period. That's obviously a bug, but it doesn't matter. We wait a little while, wait for a rising edge on the clock. After the rising edge has passed, we will then turn off the reset signal. Free running clock. Every time the simulation ticks once, this thing will advance. What do we got going on down here? We already looked at this. Every time there's a negative edge on the clock, we update the data values that are supposed to be stable for the next positive going edge. We talked about strobe before. This will print out the stuff at the end of the simulated period after everything that happens on the negative edge. The clock is done. So we can watch the counter. If it's reset, the counter is set to all ones because on the first rising edge of the clock after the reset is done, the counter will then tick to 0 because all ones plus 1 will overflow, become 0. That's what that's all about. And when we're not reset, every time the clock ticks on a rising edge, the counter is incremented by 1. All right? We can watch all that run during simulation, print everything out. What do we got? This is going to be a misleading, yes, the big endian, little endian jazz. Remember how that works. So what we're going to do is we're going to say, look, if the counter is less than the message length number of bits, then enable is true. And enable is what goes into the CRC. We talked about that before. Whenever enable is true, the index is equal to message length -1 minus counter. So let's think about that for a minute. The counter starts off with 0 after the, on the first rising edge after the reset. So what happens for index is going to start with a very big number. It will equal 9 times 8, -1, and then -0. When enable's true on the first rising edge of the clock. And it turns out that is the leftmost bit of the leftmost digit in here. All right, it may not be super obvious, but remember, this is just a bunch of bits all laid out one after another, and these are all going to be big endian bitwise. So message length -1 will be a 0 in this thing here because it's a hex 31, and a 3 is 00110001 in binary. So message length -1 is a 0. Message length -2 is a 0. Message length -3 is the 1, the first bit of the hex 3 in the hex 31 that represents this ASCII 1, okay? And then when you get all the way to 0, it'll be the least significant bit of this byte at the very far right end of all these bits here, which is a 3-9 in hex, so it'll be a 1, because 9 is an odd number, okay? So that's what this index will traverse through from, the most significant end of each byte to the least significant end of each byte, which is why I call it bitwise big endian order. So that's what this is going to do. It's going to just count from the biggest value down to 0 and go from left to right through all the bits in the array we saw above. Now, the one down here, we want to say the reflected one. This is going to count in a weird way. This is going to be useful to watch when you run this simulation. 8 times index over 8 plus 7 minus index mod 8. Okay, what this is going to do, when you watch the simulation run, I'll leave it as a test, the viewer, just deal with it. This is going to count from, what it's going to do is it's going to count from message len minus whatever it's going to be, 7, which is going to be a 1, because this is a hex 31. And the order in which we want to send the bits is little end to big end for this first byte. And then we want to leap over to the little end to the big end of this one. So it's going to count like from the right to the left of the first byte. Then it's going to go from the right to the left of the second byte. Then it's going to go from the right to the left to the third byte, and so on. Okay? So it's going to go little end to big end of each byte as it goes. All right? So that's what reflected means on the input. And it really means the same thing on the output as well, but you don't have multiple bytes coming out of it. You just have one single value that we'll see gets flipped around and reversed in that generate loop we'll look at in a minute. Okay, so we have two different indices. One of them is just going to go from the far left to the far right in order, and the other one here is going to kind of zigzag and go from right to left, right to left, right to left, and make these leaps to the right. And you'll see these two values printed out in this strobe up here, the blah, 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 index and IX ref counting when we run the simulation. You'll see how those count, okay? The data is going to be the MSB first, the non-reflected order based on the index counter, just from far left to far right. And the data reflected one is going to use this other weird index that's going to jump around and send the least to most significant bit of each byte as they arrive. All right, we know what ready will equal counter is this. So what we're going to do is we're going to generate a ready signal for ourselves to let the simulation know when it's done. The CRC doesn't know. It's just taking one bit at a time. The CRC is always outputting all the time. It doesn't know when it's done. The guy who's using the CRC generator knows it's done, and it will be done when the counter is equal to message length. That's the clock that follows the last data bit that's transmitted in there. So we're enabling it as long as we're not equal to message len. We are ready when we are at message len. And because counter just free runs all the time, whenever enable is true, this thing will go ready at the very end of the simulation, okay? Actually, I misspoke. This thing free runs all the time whenever we're not reset. So that's fine because the simulation I happen to know doesn't go over 256 bits worth of data. So this is a little hokey, but it's good enough for the test bench that we're dealing with, right? In other words, this thing will count past message land, which I do in my mind remember. That's why I checked my words here. This will cause ready to become true for one clock period and then go false again. And if you keep clocking this test bench forever, it's going to screw up and wrap around the 256 bits and go nuts. So that's just the nature of this thing. You need to make sure you stop it before you send out too much data. Okay, and we'll see how it stops in a minute down below. So this thing is going to enable it up to this many bits. The ready signal will go for one period after it gets to message len, and you'll see it stops down here after this. Okay, so I got a couple of different, initial blocks in this free running always combo block to calculate all these values, right? So what does this one do? He says, wait until ready goes on a positive edge. Well, ready goes positive right here. So this initial block will wait until all the bits have been sent into the CRC modules and the ready has become true. And we know if this is true, then enable has to have become false at the same time, because that's the nature of these two operators, right? So when all that is done and we have a clock that made this thing go ready, what we do is we wait a little while. I don't know why I do that. There's really no reason to do that. And then we point out all this stuff. And this is a test bench that says, look, CRC 8 better be an F4. This one better be DA, and so on. These are the values that I got from here. CRC 8 is F4. And Mr. Whack-A-Mole is 25, and so on. Here's your 25 for there. Okay? So I took the 1 through 9 data from the website. I built the CRC generator that I believe is going to do the right thing. And then I run it and clock in all the bits based on whether I want to send them in reflected or not, based on which one I'm instantiating up here. If it's supposed to be reflected, I use the reflected one. If it's not, I use the non-reflected one, okay? And then when all of them, they're all going to get done at the same time because they all have the same data going into them and they're all have the same length of the polynomial. And therefore, when the thing becomes ready, I know that the CRC out value is immediately presenting the current CRC value of all the message bits received so far, and I can simply say CRC 8 equals the current output value, and then I can print a true or false, a binary, yes or no, 1 or 0. If these are all 1s, then all these things equal the values they're supposed to be. Okay? So let's go and run this and see what happens really quick. Would you just take, make CRC VCD is the target that'll run the simulation and generate the VCD file for plotting the graph if you want to plot it. But I don't really care about plotting it. To be honest with you, we want to look at these values. Look what happens in the data bits one at a time that are going out. You can see the reset's true here. The enable then goes true here. So this is the first bit that's sent into it. And in the most significant bit order, remember it starts with an ASCII 1, which I said was a 31. That's 0011 0001. This in ASCII, in big endian binary first, that's your 31. If it's reflected, it goes the other way. There's your 0011, that's the 3, and there's a 0001. So these bits go out backwards. Look at the way the indices work. I'm either going to go from 71, 70, 69, all the way down to 0, or look what happened here, right? This is the first 8 bits. You can see the 31 here, and you can see the backwards 31 there. This is going to go 71 down to 64, and then move to the next one at 63 and keep going. The reversed one, the reflected one, is going to go from 64 to 71, which is why this bit here is the value you see up there and so on. Okay? So this is reflecting. It's just simply sending the bits out in the opposite order on a byte basis into our CRC generator. And this is done on a byte basis because that's the width of all of the test data because we're sending ASCII. All right. Now, as you saw, all these get checked against what they're supposed to be, and it'll print a 1 on the right if it's got the right value. Otherwise, it'll print a 0. So these all checked out based on me instantiating it right, me sending the data out in the right order or reflected order, and all this other fun stuff. Okay? Which is pretty cool. I was very happy once this thing started working. We can also run the other one, make CRC CD, and you can see I only have 2 instantiated test cases there, and they both come out to 1. They're ARC and CDMA 2000. This has obviously same name, right? There's an 8-bit CDMA and there's a 16-bit CDMA 2000, okay? So these are the check values and they matched out as well. You can see some X's in here because in the test bench code, I say if the enable is not true, I put an X in the index, and that'll be true up at the beginning as well. So that's just a little reference there if you didn't follow along and notice it until now. And you can again see that the reflected and non-reflected values do the same thing here, all right? So they're flipping the most significant bit all the way down, and this one's going 64 to 71, and then it'll go 56 up to 63, and so on, okay? So that's what reflecting means. And the reason you want reflected ones is because if your data arrives in a natural big Endian bit first, you want to use a CRC that takes them that way. Otherwise, you have to have more circuitry to flip it around. In our case, the flipping makes the test bench more complicated. But in reality, it depends on the circuit you're using. And if you pick the wrong CRC, you've blown it. And I've done that myself, and quite recently, and chose a CRC that is reflected and it should not have been reflected, and so on. So yes, now you know how to do it, and I've reminded myself again, oh yeah, I picked the wrong one. You need to do it right, okay? If you want to be efficient. Otherwise, you have to buffer up everything and then reverse it and build more circuitry and write more Verilog and all that other fun stuff. So let's look at this generate. We've talked about the whole thing. We gave you the context and show you where you can get the background. Let's look at this generate statement. So back to basic Verilog here for a minute. The idea here is sometimes you have a lot of stuff that's like the same thing over and over again, and you'd have to type it all in. In this case, if I wanted to have a module that generated an 8-bit CRC and I wanted the output reflected, I'd have to write something to flip all the bits around. And if I did that, I'd have 8 assignment statements here. And that's not a big deal, and it'd be a heck of a lot easier to understand than what this is if you've never seen one before. You might argue, I'm an idiot. Why didn't I just do that? Well, the answer is because I want to be able to use the CRC module for 8-bit CRCs, and I also want to use it for 16s and 32s or whatever I want. Now I got a problem. How many assignment statements need to be in there? Well, now it depends on how many bits there are in the CRC I'm generating. Okay, now I need a way to programmatically generate lines of source code before they're compiled by Verilog. So this is a really simple, straightforward thing. If you're going to need, what I'm going to do is I'm going to write a for loop, and I'm going to say, I'm going to count from 0 up to the number of bits. I want to generate an assignment statement for each bit in my CRC register. That makes sense. Okay, so what I'm going to do is I got to write a for loop and go from 0 to whatever n is, and that'll be 8 or 16 as the case is in the 2 test benches. And after each time I do this loop, I'm going to add 1 to j. And for some reason, the infinite wisdom of the designers of Verilog, I cannot say ++J nor J++. I have to write it out longwise. I don't know. This was invented many years, at least a decade after C, and why they saw fit to base it largely on a C-like grammar, but not whatever. Okay, one of the many pet peeves I have, I'm constantly doing this, a la C, and getting errors. So keep in mind you have to write this out a long way. Now, a new type of variable, a genvar. These things are used in generate statements, and they're not wires, they're not regs, they're not signals. They don't become part of the net list of the circuit. These are around for the sole purpose of being able to use them in these loops that are, really fancy macros are going on here. So that's kind of what's going on. So I'm going to do from 0 to 7, because it's less than 8, from 0, 1, 2, 3, 4, 5, 6, 7, if bits is set to 8. I'm going to run through here, and then it's just simple math. If, okay, so I'm going to say for each one of the bits, CRC ref, this is the reflected output, sub j, which is going to go from 0 to 7, is going to equal, if I need to reflect, if I need to reverse them all, then I need to set, for the first pass, CRC ref sub 0 needs to be equal to CRC reg sub 7. 8 minus 1 is 7, minus j, first time is 0. Okay? That's what will happen if ref out is true. If ref out is false, then cref j is the register of j. Don't flip it. So this is going to generate this many assignment statements, and in this application, I'm going to set CRC ref 0 when I want to reflect it to CRC reg 7, and then I'm going to set CRC ref 1 to CRC reg sub 6, and so on, right? So this is just going to flip them all around, reflect the order, if this is true. Otherwise, it's going to pass them straight through, in which case all this will literally accomplish nothing. And the beauty of all this is that the entire thing will be optimized out no matter what anyway. It's just a matter of getting the right bit numbers in all these variable names, so when the compiler runs, the wires are connected correctly in the FPGA. This will use no LUTs whatsoever to do this, okay? It's just which value from the CRC reg, which bits go to which output bit ports, because the CRC ref is going to be used down here. We already saw that before, after the XOR, and then assigned to the output of the module. Okay, so do you want to go from left to right or right to left? That's all that's going on in here. Okay, and if ref out is false, this entire thing accomplishes nothing whatsoever. Okay, so this is designed to be optimized away in this particular application. That's not always what generate means, no way. But just by the way, I'll observe that's what will happen in this scenario. Okay, and it's going to be optimized out because ref out is a constant. It's a parameter, so it's an immutable constant during the compilation process for each instantiated module. All right, and so is XOR out, by the way. If you think about what this means, if you're going to XOR the output of this, reflected or not reflected output with some value, all you're really doing is flipping all the bits that have ones in the vector positions of this XOR out parameter. And because this is a constant, it won't use LUTs and create XOR gates and all that other fun stuff. It will simply invert the output of the CRC ref in the circuitry up here. It will, if you think about it, a lot of this is not going to be used anywhere else. It only calculates it to come out of here. And inside the FPGA, a lot of times you have these true and inverted outputs of all these D latches all over the place inside of the FPGA. So you usually have the true and the false ones available at all the time. Anyway, So it should be able to do this without actually using any more LUTs. Although that would depend on the FPGA very heavily. They may or may not have the ability to just generate both the true and false outputs from the LUTs that are used up here when they're doing all this fun stuff. Okay? But that all, again, it depends on the FPGA. And if your XOR out is 0, which is perfectly fine, I don't know if that actually helps or hinders you in any way. Like the init thing does. If you have a 0 in init, it'll mean something different than if you had a non-zero, as I explained earlier, and as I believe Ben Eater talks about in his video as well. All right. So if you don't want to do this, you can just put a 0 in there. Then this literally gets optimized away. And that just goes right into CRC out. Okay, so that's how the whole thing works. That's the purpose of generate statements, which I wanted to hit as a general Verilogism in an application that is relatively simple. This is certainly understandable. If you sit back and think about it for a while, you can get the theory from Ben. Just keep in mind that these are very common. This is the way that you'll normally see it done inside a real circuit because the output value is ready immediately, as opposed to, and Ben talks about this in his video, calculates a value and then he sends in a bunch of zeros for it to finish the calculation. And then you have your CRC, okay? So a couple of things hit here, 3 things. First, there's 2 different ways to calculate serial CRCs in general. This is generally how it's done. You have to deal with whether or not the input is reflected, and that would normally be set to the way your natural data arrives in an optimal use of a CRC algorithm. You want to bring it into this bit shifting style, if you're going to use this style, in the native order that it arrives. So pick one that works that way. You may or may not need to reflect the output, and you may need to flip some of the bits on the output based on whatever you agree with the third part, your other side of your serial connection. You got to agree on all these parameters, and these are all very standard CRCs. Ben talks about, to some degree, what makes a good CRC polynomial and not. I've beat the init up in this discussion, and Ben talks about the polynomial, what it means to have an 8-bit polynomial, a 16-bit polynomial, a 32-bit polynomial, and mathematicians can bend your ear on what makes 1D a better or worse polynomial than a D5, and so on. That's not something that's in my zone of interest. I'll let the math guys figure that out. There are some that are better than others. That's all there is to it. The number of bits in the polynomial have to do with the nature of errors that can occur as data arrives. I'm kind of thinking about Ben's video when I throw in these side comments, because I don't think he really got into why you want a bigger polynomial in some cases and so on. I mean, obviously you need more circuitry to calculate a bigger polynomial, and there's a cost. What's the return on that investment? And in my opinion, what you need to do is think about what Ben mentions in his video is that if I have a 16-bit polynomial, I believe you can detect a sequence of bits that are all corrupted in a row up to the size of your polynomial. But if you have more bits that are corrupted than are in the number of bits in your polynomial, then you may not generate an error, because you can get a false positive. But mathematically, you can prove, based on what polynomials you choose and how many bits there are in them, that you can detect errors that occur in a small cluster. And therefore, it is the nature of CRC. You see these used a lot in serial data communication, where a lightning strike can create some static noise while bits are being transmitted. And they may be flipped in a small group, while all the others that came before and after are probably okay. That's also true on disk surfaces. Any magnetic medium has that nature. And a CRC works well for that, provided that your polynomial length is big enough to span whatever the total number of bits in a row might be corrupted, so that you can detect that error. Now, it's not to say it won't be give you the wrong CRC if you have other bits wrong, that are corrupted as well. But you can guarantee that if you have a group of bits that are corrupted and they're all close enough together so that the distance between them is less than this value, is what I'm trying to say there, then it will generate a value that doesn't match the reference value that the transmitter, the originator of a message, would have calculated themselves. Okay, so that's how you detect. That's how you decide how many bits you're supposed to have. And if you think about it, that is also why you need to make sure that you either reflect or not based on the arrival bit order. Okay? Now, I'm not saying you need to turn your bits around. What I am saying is pick a CRC where both ends agree on whatever you're going to use. And if you're going to send data bits in big endian order, each byte in big endian order, choose one that's not reflected. Okay? And the reason you want to do that is remember what happened when we ran the test bench. If all your data bits arrive in big endian order, this is the order in which the bits will arrive from whatever it was, 71 down to 0 in this order. If you choose one that's reflected and the data arrives in big endian order, then you're a dingbat, because what you'll do is you'll save up 8 bits, then you'll reverse them, then you'll apply it to your CRC calculation. Look what happens here. If you have a bit here that's wrong, and that one, and that one, and that one, and that one, and so on, look at this. You do not want to flip them around and then calculate it. You want to process them in the native order that they arrive. And if you're bringing in like an RS-232, a UART style thing, you're going to get the least significant bit first, and then you're going to get the most significant bit. Okay? I'm doing this backwards. There's the 1 from the 31. There you go. This is it right here. There's a 31 in little endian order, and there it is in big endian order. So what would happen is if you had a sequence of bits that were flipped, you don't want to read them in this way and then process the message in the other way. Because when you corrupt a sequence of bits, you might corrupt these bits right here. But if you read in a byte and then reverse it, and then you process your bits, then these 2 bits will be far away in the CRC math from those, and you may not detect that error. You following me? If you're not, pause it and rework this out. You want to make sure that if you receive bits in this exact order, this is the order that they go into your CRC generator. If you receive them in this order, which is reflected, you want to, again, process them in the native order that they arrive, so that if you have adjacent bits that are all corrupted in a row, which is the nature of magnetic medium or a serial cable or something like that, you want to feed them into the CRC logic in the native arrival order. Otherwise, you're not going to get the optimal value out of the CRC. You can get false positives. And this is one way you can make it suck more than it needs to. So don't do that, okay? So Ben doesn't bring that up because he doesn't really talk about this in his video, because he talks about the basics, and this is then you take the basics and then you apply them to your specific situation, where things like this, these considerations start having to come into play. I hope all this stuff makes sense, and you can actually make use of this and other CRCs now and make intelligent decisions on how to apply this stuff. It's really cool. The circuits are super simple. The math, go look at Ben's video. He's literally, it's a really good job talking about why it is, how it is, and all this other fun stuff. And you'll see what I'm saying is true if you understand that basic context below. And if you understand the nature of Ethernet, which sends big endian first, versus UART, which sends little endian first. That's why we got all these options, and that's what they mean. Thanks for watching. I'll see you next time.